How are you guys? I hope you're doing well, huh? So, similar to the previous review, well, I'm gonna go all I'm gonna explain the whole objectives of this module. We will tackle it together through some examples, and at the end, I will share. I will open the floor for some questions, so you can ask me. For this lecture, I will take attendance because I'm doing it on the synchronous time, but I really don't like forcing rules, okay? So we will see what will happen, okay? Okay, so at any time, if you would like to ask, please chat as well as raise your hand. If you're not familiar with Zoom, if you're not familiar with Zoom, familiarize yourself. I gave you like how many? Okay, I gave you 10 minutes now or 15 minutes. Okay. Now, after you raise your hand, I'm gonna unmute you so you can ask me. Okay. All right. So let's get started. Share. Yeah. Okay. So do you see the screen? Yes? What? I'm coming back from the space. Yes, good. So you might ask yourself, oh, this guy is explaining ones and zeros, and then he jumped to explaining Boolean, and he's adding, and he's asking us, no, that's not an and, this is like an or. So what the hell is going on with this course? Okay. In life, guys, you can describe any problems either by a mathematical model, or you will describe a problem using a program, okay, using an algorithm, okay? So anything in life can be done through a systematic plan. If you ask your mom, if you are a girl and ask your mom how to do a muffin, the recipe to do a muffin, those plans called an algorithm, okay? And if you are a guy who got stuck on the road and you don't know how to change the spare tire, you will ask your friend, or you ask your dad, and he will give you the steps. Those steps are called algorithms. If you translate the algorithms through a mathematical notation, now you're dealing with a math model. You can skip it and you can program it. Now, I know that I'm talking all over the places, but the thing that I'm trying to explain is that we want to rewrite any problem in a way that can be solved using the computer, okay? Or that can be solved by designing a controller that will do that job, okay? So as an example, so let me, okay. That's okay. I waited so many times, and now there is some people joining. So you have an example here, and at this example, you are supposed to design a logical circuit that automatically operate a car alarm. So let's suppose that you yourself, you're working at the automobile companies, and you want to design a simple controller. And this controller is to give an alarm as long as the following condition is either satisfied or is not satisfied. So the alarm will go off if the alarm system is activated, or any of the two doors or the trunk are open, or the vibration sensors is activated and the key is not in the ignition. So this problem can be described using Boolean algebra, because Boolean algebra is part of the mathematical science. But the difference here that the input or the variables that you can grasp from this problem will be either like satisfied or not satisfied. So in other words, it will be either true or false, on or off. So we're revolving around the same thing all over the place, which can be described via binary values, so 0 and 1. So to make it easier on you, I grasp myself the input, okay? Okay, scene, buddy, change your name. I don't want to see scene, okay? I want your full name. If I don't see any full name, at the end of the course, you will beg me to increase your grade from 79 to 80, so you will get an A minus. I will not. If I do not see your name here, I will not. Okay? And okay, let me jump from that. And when I ask you to do the exercises, those exercises just to familiarize you with the way that the exams will be done and how to upload your solution, because your solution is supposed to be like uploaded on Google Drive. And for those who collaborated with my exercises, again, I'm gonna look at the end of the course and see who did and who did not. And who did, I'm the boss. I can increase the grade. I can apply a bonus for him, okay? Okay. Yeah, I'm really sorry for that. Yeah, let's put that here, put that here. And okay, so now let's read the question again. The alarm will go off if the alarm is activated. So A. So the student who asked me is correct. So A has to be like that's it. So F will be equal to A, and A is supposed to be ANDed with all the doors. So we have D plus D plus P plus T, okay? And we have or, if the vibrator sensor is activated, V, and the key is not at the ignition, K prime, okay? So with that being said, the way to implement it, A, ANDed with, I have here to have an OR with DPT, okay? So those are OR, and this is an AND, okay? And I have here V, and K has to be inverted. Here, this is another AND, okay, and the end I will have an OR. Perfect. Okay. Yes, Lilia. Go ahead. How do we know which one we should choose? Okay, go read the question again. The question says that the alarm will go off if the system is activated and any of the doors or the trunks are open, and there is a comma. Exactly. Thank you, Ethan. There is a comma. The comma means we have to start another expression. Okay? Okay, let me admit those. Admit all. Okay, so let's move to the other one, okay? Okay, boom. Okay, guys, if you another thing that has been addressed throughout this chapter or this module, in other words, because I'm mixing two different things, is the logic gates. So we have three fundamental logic gates, which are the AND, the OR, the inverter, okay? And you might saw on your textbook that we have something called the buffer. Is the name speaks itself, so you will not do any modification for the variable, okay? So the buffer is an complement of the inverter, okay, guys? Now, when it comes to the NAND and the NOR, they call the functional complete gates, because I told, like I've shown you on the recording, that any Boolean function can be implemented with just NAND or with just NOR, okay? So if you go to Amazon now or to Canadian computers now, and you want to buy a solid state drive, you will see that it's built from a NAND, okay? NAND controller. So all of the gates will be built by NAND, because that will make it cheaper. Instead of buying multiple component to implement that function, something like, you know, the function that we have, the function that we just designed, we can implement it with NAND only, okay, or NOR only. Okay, so the exclusive OR and the exclusive NOR are gates that can be implemented using the fundamental ones, okay? And both of them, actually, they can be implemented using the fundamentals, but like the functional completes are easier for fabrication and manufacturing, okay? So when it comes to the OR, it stands for inequality. So it will be used to detect if an error happened somewhere. So suppose that you're compressing a file and you want to make sure that your file has no problem. So what you have to do, like the hash file of your file at a current machine can be XORed with the hash file after you send it. And if they are unequal, or if there is like a light that will show that it's high for sure, then that means your file is corrupted. The same problem can be solved with an XNOR. The XNOR, they like will give you high as long as both inputs are equal to each other, or they have the same Boolean level, the same logical level, okay? So let's go here at your textbook and see how can we, you know, like describe those logical gates in terms of Boolean functions, okay? So as you can see, F0 indicate to what? F0. So regardless of the input, F0 is 0 all the time. That means F0 is equal to 0. Now in lab 2, you will be asked how to implement a 0 state. So simply F0 can be implemented in digital electronics by attaching it to the ground, okay? So let's take a look at F1. F1 here is basically an AND, because it's 0 all the time unless both of my inputs are equal to 1. That's why it's an AND. F1 is an AND, okay? When it comes to F2 here, F2 is an inhibition. Why it's called an inhibition? Only give you 1 as long as this case, which is when X is at the true state, but not Y, okay? F3 here, F3 is called a transfer. Why? Because X at all times. So it can be like described as a transfer. Those words are not important for me. The most important thing is capturing the Boolean operation, okay? Now, what about F4 here? F4 is an inhibition, but it's not, it's the inverse one. So it's when Y is active, but not X, okay? Now, what about F5? It's simply like a transfer of Y, all right? And so on, guys. That's it. Like, you know, you go and you look at F6. F6 is equal 0, 0, 1, 1, 0. You look to the input. You need to describe the function in terms of the input. What the input you have here? So we have X and Y, and they're equal to, like, the function is high here is 1 if both inputs are not equal to each other. So that's remind us with what? With the XOR here, okay? That's remind us with my XOR here. Therefore, F6 can be simply described by saying F6 can be simply, it's an X exclusive OR with Y, okay? So do you have any question? Is the buffer same as the wire? Yes. The buffer is like a wire. Yeah, but there is something I want to, like F15. I love it. I love F15. So F15, so regardless of what is my input, F15 is always 1. So what does that mean? That F15 can be implemented by just attaching it to a positive voltage. Yeah, you love F15? Yeah, okay. VCC. Okay. At lab 2, you will be asked to simplify a function, and I'm like, you know, I'm giving you a hint that function at the end will be equal to F equal to 1. So how you're gonna implement it on Quartz? What you have to do an output pin to simply, like let's suppose that this is an output pin, okay, and that is F. So you don't need to do like to use like the input, like for instance, you have A, and what you have to do is you OR A with the inverter of, like, you know, that's A, and you OR it, okay, to get 1, because F equal to A plus A prime, that is equal to 1. So you don't need to do that. What you can do is simply that output pin here, which is called F, you go at the logic, you look at the primitive, you look for something called VCC, okay? So VCC indicates the voltage, the high voltage, okay? So in our case, when we're dealing with the current computers, it's plus 5 volts, okay? Okay, guys. So do you have any question? We'll leave the question to the end, okay? Yeah. Shown you on the lectures. Let's suppose that you have a function F equal to 1, like the one that we just liked, okay? F equal to 1. So F equal to 1 can be implemented with just VCC, okay? And some guy, he's trying to be catchy, and he can say F can be implemented by A plus A prime, okay? So which one do you think is simpler than the other? Of course, this version, okay? This version. Yes, that's it. So we need to use those postulates and the theorem in order to get the simplified version of a Boolean function, so we can minimize the cost of implementing it, okay? Now, let's assume we have.
Professor, your mic is muted.
Professor, hello? Your mic's muted.
Can you deafen us?
No, I don't think he can hear us, man. This sucks.
She.
Can't we just type in chat?
If he's looking at his chat,
Professor, you're muted right now.
I don't
he's
think
still
he
concentrated. We're trying to catch his attention.
we can't hear you. Oh. Maybe someone send him an email.
Professor, we can't hear you.
Sorry. I'm really sorry, guys. Okay. So again, we have this example and we would like to simplify it. Okay. So the example is A, B, both of them are primed, and we have A prime plus B, and then we have B prime plus B multiplied by 1. Okay. So basically this one, B multiplied by 1 is B, and B plus B prime, according to postulate 5, is equal to what? 1. So anything you multiply it with 1 will give you that thing. So if you have x multiplied by 1, this will give you x. However, if you have x plus 1, this will give you 1 all the time. Okay? So basically this terms is gone, has been omitted. Now, this is the interested one. Here I have A, B, both primed, and I want to change it. So I can do De Morgan. What De Morgan says, that I can change the operation as long as I distribute the complement. So A and B, both of them in prime, will be equal to A prime plus B prime. And that's what I did. Now, what I'm going to do is I'm going to use the distributive law to multiply A with this here and with the other variable here, and B will be multiplied here and will be multiplied. B prime will be multiplied with B. So when I multiply A prime with itself, that is equal to A prime. Okay. Then when I multiply A prime with B, this will give me A prime B. All right. Okay. Now B prime with A prime, this is B prime with A prime. This will give me A prime B. Okay. And B prime, A prime, B prime, A prime, B prime. And then B prime with B, this is B prime with B. So B prime with B, this will give you 0. If you multiply the variable with its complement, that means, or if you AND it, that means you will never get nothing. You will get 0 all the time. So this can be rewritten as 0. This can be rewritten as 0. So I have here A prime plus, no, A prime B plus A prime B prime. Okay. So what I have to do is to take A prime as a common factor. I will get B plus B prime. This can be eliminated by a 1. Okay. And then I'm going to get A prime. So this whole function, okay, is being simplified using the postulates here to just one literal, which is A prime. Okay. Okay, guys. So let's move on to the another subject we covered at module 2. Okay, guys, let's keep the questions to the end because I'm using 2 computers at the same time, and that's why it's very hard for me to keep up with you, okay? At the end, I will share it on just my main station, and we will go over the solution, okay? Okay, so let's suppose I have here A ORed with B, and then I have C here, it's ANDed, okay? So this digital circuit can be what? This digital circuit can be described by either one Boolean expression. What is the Boolean expression of this circuit? F equal to A plus B, both of them ANDed with C. Okay? That's one way of describing it. Another way of describing it is via the truth table. So you have 3 variables, A, B, and C, okay? And what you have to do is you look how many variables, how many input variables, A, B, and C, and this is F, okay? How many input variables that you have. In case you have 3 here, what you have to do, your truth table will contains 2 to the power 3, which is equal to 8 rows. Those rows will be translated into unique combinations of the variables at their true state or at their complement states, okay? So how can we describe 8 possibilities? The 8 possibilities can be described simply if I take A as my most significant bit. We'll start by describing that is one possibility, which is what? Which is the Boolean notation of 0, okay? And this is 0, 0, 1, and then 0, 1, 0, 0, 1, 1, 0. No, now I'm done, okay? I covered everything for those 2 digits. I have to move to this digit. So 1, 0, 0, okay? And then 1, 0, 1, 1, 1, 0, and 1, 1, 1. So that's one way of writing those combinations, okay? The other way of writing it is, let me go here, okay? The other way is, what is my least significant bit? The least significant bit will change frequently, okay, in a frequency that is the highest among all the other variables. So this will be 1 times 0, 1 times 1, 1 times 0, 1 times 1, 0 and 1, 0 and 1, okay? So how many times should I repeat that? 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Now, when it comes to this variable, it will change its state in a way that is doubled the previous variable. So this should be 0, 0, and this will be 1, 1, 0, 0, and 1, 1. And similarly, A should change its state in a frequency doubled the previous variable. 0, 0, 0, 0, 1, 1, 1, 1. So here we change every 2 rows. So here I have to change every 4 rows, and so on. Okay, so we go here to the function, and we say that this function is equal to A plus B and C. So 0 plus 0, this will give you 0, regardless of what will happen, okay? 0, 0, 1, this is still 0. 0, 1, 0, that is still what? 0, okay? Now, 0, 1, 1, that will give you 1 because A or B, which will give you 1, or and with C, this will give you 1, okay? and this will give you 0, this will give you 1, this will give you 0, and this will give you 1. Okay, so this is another way of describing your digital circuit here. Okay, in addition to what? To the English description. So we can say here that we are ORing A with B, then the resultant is ANDed with C. Okay, now we should agree in a standard way to describe my digital circuit. That standard way can be either a sum of a product or a product of sum. So how can we get the sum of the product? Sum of the product, we look at our truth table here, the truth table, and we examine when the table was equal to 1. Okay, now each row can be described as what? This is M0, M1, M2, M3, M4, M5, M6, and M7. So my function F, my function F is high at M3. Okay, what is the code for M3? Using a sum of a product. So M3 has to be expressed in a product of my variables. My variables are A, B, C. When A is equal to 0, that means that variable it's at complement format, at its false format. Okay, that is what? 0. Okay, 0 logic. So M3 will be A prime, and B it's 1, so it's at its good format, true format, so it's B and C. So for M5, it is A, because A it has 1, and B prime and C. And when it comes to the last one, which was what? The last one, which was M7, okay, which is A, B, and C. So my function F is equal to M3 plus, okay, sum of product. I sum all these terms, M5 plus M7. So in other words, can be described as what here? Sum of 3, 5, 7. This notation of describing the digital circuit is called the canonical sum of the product format. Okay, at which 3 will represent the min-term 3, and 5 will describe the min-term 5, and 7 will describe to min-term 7. Some guy now will ask me, I'm not seeing the chat because I have a lot. Some guy, he will say, okay, what do you mean by a min-term? The min-term is the way that you describe each row in your truth table. Okay? So that is for the min-term. Okay, let's forget about this example, and because okay, I made a mess. Let's describe this example using the product of sum. At the product of sum, guys, so instead of looking for the function when it's equal to 1, we will look at the function when equal to 0. You know what? Okay, let's do it when let's do it for the sum of product, and I will show you that they're equal to each other. Okay, so here F is equal to 1 here, 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 and is equal to 1 here. So F can be described as the sum of, that is what? M1, 1, and then 4, 5, 6, and 7. Okay. So if I'm gonna describe this function using the sum of product, the canonical sum of product format, I have to describe it like using this equation, where you can rewrite it in terms of the min terms. Okay, so you will say that is A prime, B prime, and C plus A, B prime, C prime. Okay, so please pay attention to here. So here I would like to describe 0, 0, 1, this row. So that is A prime, it's 0, B prime, it's 0, and C is 1. Okay? And here I would like to describe 4. So that is 1, 0, 0. Okay? And so on. Okay? So if I'm going to describe this function using the sum of product, I will have 1, 2, 3, 4, and 5. 5 terms. And in other words, 5 terms, and they are described as a min term. But is there any way to save the implementation of function f? The answer is yes. So I have to explain it using the 0 format, the negative logic. So if I describe it as the negative logic, I'm winning here because I have only 3 terms. Those 3 terms can be rewritten as a max term in a way that that max term is simply describing a row at the truth table at which the function is equal to 0, and the row can be coded in a way that is a sum of my variables, and at the end they will be producted. Okay, so let's describe this function. So the function is equal to 0 at this row, that's m capital 0, and here m capital 1, 2, and m capital 3. Okay, so m capital 0 can be rewritten as product in a product way, product of sum. It's A plus B plus C. Now some guy will ask me, okay, how come now they're not complemented? Because guys, here we're looking for what? The negative logic, okay? Which is the false logic. So like in life, you can describe things either by saying, okay, I own this house, or you don't own it. Okay? So it's easier for me to negate the description of this truth table. So I will describe it with I will implement it with these terms. So when I look for it, like at the product of sum, when I look at the 0, I will keep it as the true state, and when I look at the 1, I will represent it as as the complemented state. So that is for m0. Now instead of here, guys, you remember what we did here? We did an addition. Now no, this whole term is producted, is ANDed with, I have m2 here, so that the function f is equal to 0 at m2 as well. m2 can be described as, now look at this, a is at the 0, so it will be written as a, plus b is at the 1, is coded as 1 here. So what I have to see to do is to negate b. B prime plus now c is at the truth at the 0 state, so it will be written like this. And then the last one is m3. m3 is a plus b prime plus c prime. So this can be, because it's like each term here is described as a sum, and then all of them are producted, can be described as a product of sum, and it will be what? It will be 0, 2, and 3. And have you noticed something, guys? The product of sum, the max term is always what? The complement of the min term. So we have here 0, 2, 3 for the max term, and we have 1, 4, 5, 6, 7 for the min term. All right? Now, I'm gonna move for the last question here I have. And this question will make things more clear for all of you, and then we'll open the floor for what? For one-to-one questions, okay? However, I'm gonna take a break of 1 minute. So this type of questions, you're supposed to what? You're supposed to design that a circuit, and if we compare it to the first one, this circuit has been described in a different way. So if you see here what I'm saying, that in this diagram, this box, at the end of the day, this box is sum and or. We don't know how we can describe it, but we look at the goal. What is the goal here? The goal is that circuit will produce true if and only if a majority of 3 inputs are true. So what's the majority? So in other words, if 2 of my variables, A and B, exactly, thank you, Tamim, are in the one or the true state, as long as we're doing the sum of product, that means what? That means F should be equal to 1. Otherwise, it's gonna be equal to 0. So how can I solve this kind of a question? So at the end, that question mark should be some and or, and this is what I'm gonna do it, how I'm gonna find it, okay? So first, the step 1 is to set up the truth table, okay? Because, you know, like this statement is fake, you know? I have to set up the truth table in order for me to capture all the possibilities. Otherwise, like I will miss one term, okay? So the truth table here, I have 3 variables, A, B, and C. And this is 0, 1, 0, 1, 0, 1, and 0 and 1. This is 0, 0, 1, 1, 0, 0, 1, 1. This is 0, 0, 0, 0, 1, 1, 1, 1. All right, guys. Now, so let's read the question again. The box represents a logical element which produces a true output if and only if the majority of the 3 inputs are true. So here, my function will give me 0 because none of them are true. And here my function will give me 0 because just C is at the true, whereas the others are equal to 0. Now, at this case, at this row, still 0. Now look at this one. I have 2 variables at the one state, okay? And that's why I'm gonna put 1 here. Now this will be equal to 0. Now here I have this one and this one. So 2 of them are high. So what I have to do is I'm gonna put 1, and here it's be equal to 1, and here it's gonna be equal to 1, okay? So this row can be described as M0, M1, M2, M3, M4, M5, M6, and M7. So function F can be described using the canonical sum of product standard as the sum of what? Of 3 and the sum of 5 and 6 and 7. Okay? So how can we get that? It's basically A prime B C plus. What if we have 4 inputs? It's going to be 16. Okay? It's going to be 16 possibilities and the same principle. A, B, C. Okay? Plus A, B prime, C, plus A, B, C prime, plus A, B, C. Okay. This one is the code for the 3. Look at this. At the 3, A at its 0 format, because we're doing here a sum of product. Okay? And B and C are at 1, so they are the true format. Okay? So, can we simplify this output? Yes, we can simplify it using Boolean algebra for now. So, how to simplify it? How can I simplify it? What should I do? I can say this can be rewritten as what? It can be rewritten as A prime B C plus A B C plus A plus A prime B A prime B C plus A B C plus A B prime C plus A B C plus A B C prime plus A B C. Now, he might ask me, you repeated ABC multiple times. Yes, is the equation the canonical form? Yes, this is the canonical form. Now this one, I repeated ABC 3 times. Why did I repeat ABC 3 times? Because I want to do the following, at which I want to take the common factor. So what I have to do here, I can take BC as a common factor, and this will give me A prime plus what? Plus A. And for these two, I can take AC as the common factor, and this will give me B plus B prime. Okay, and for the last one, I can take AB as the common factor for the last one, and this will give me what? C plus C prime. That is can be what? Deleted. That is can be deleted, and that is can be deleted. Okay, so that function f can be rewritten as AB plus AC plus BC. Okay? Now, what about the product of sum? Product of sum, and you know, guys, I might ask you to write function f. I give you this function, and this function is not at its canonical sum of product, and I want you to write it at the canonical sum of product. Okay? How? So you look at the first term. The first term is missing what? C. So if we multiply AB with C plus C prime, which is equal to 1, does it harm it? No, that will not do anything. Now here we're missing B, so what we're gonna do is A multiplied by B plus C prime, B plus B prime, and C. Okay? And here we're missing A, so what we will do is we will say BC will be multiplied by A plus A prime. Okay? because at any of these terms, let's take a look at this one. If we multiply BC with A plus A prime, that's equal to if I multiply BC with 1. And if I multiply BC with 1, it's still BC. Okay? So what you can do is you can multiply using the distributive law, multiply all of, like, you know, AB with this and with this, and then AC you multiply it with B and B prime, and then you will get this, what? This equation. And at this equation, you will, it's simply stating that that is 3, and that is 7, that is, yes, that is 1, because A it's 1, and this is 0 and 1, that is 5, that's 7 again, no problem, and this is 6, and this is 7 again. So we remove the redundant terms, and we keep just 1. So 7 has been repeated twice. We will take just 1. So we have 3, 5, 6, and 7. Okay? So that's again our sum of product. Okay? Now, when it comes to the product of sum, guys, here we look at, okay, let me delete this, delete this, delete this, delete this. We will look at the 0. Oh, no. Okay, so function f here. Okay, draw. Function f at the end, at the sum of product, was equal to AB plus AC plus BC. Now, I want to implement that with NAND only. How I'm going to do it with NAND only, guys? You have two options. Either you use De Morgan, or you implement it using the and or, and use the circuits, use the shortcut. So you have A, you have B, and you have C here. Okay, so okay, I will accept this at the exam, so no problem. So you can do, this is an and you can repeat A again. So A and C, this is an and BC, you can do it again here as an and. Okay, and all of them are OR. Okay, and this is F. So if I want to do this as an AND only, what I have to do, after each AND, I put what? A bubble. And before each OR, I put a bubble. Because this is a bubble here and bubble here. That's something similar to De Morgan. Bubble with bubble. A prime is still equal to A. Okay? So you have here as, this is an AND, this is an AND, NAND. This is an AND. Cancel. And this is an and this is an AND. Okay? And this, okay, now let's suppose that this is X, Y, and Z. Stop, man. So F is equal to, let's describe this. It is X prime plus, can you stop? Plus Y prime plus Z prime. If I wanna, according to De Morgan, if I wanna describe it, what I can do, I can make a big bar and change the operation here. So that is X, Y, Z, big bar. So what was X here? X was AB prime, Y was AC prime, and Z was BC prime, and both of them are prime. Okay? Or, guys, we can do the same thing. F is equal to AB, AC, BC, double prime here, and take the prime in. So you have to change what? You have to change the operation. So AB prime and AC prime and BC prime, and all of them are prime. So those are, this is a NAND, 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 and the whole thing is a NAND. In other words, this OR thing can be replaced by a NAND. Okay? And when it comes to the product of sum, what I have to do is I have to go back to my truth table. What is my truth table here? And describe the function when it's at the 0 state. So here, 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 and here, okay? While each one is an M capital. It's what a sum of it's a product of sum. So F can be implemented as what? As the product of sum of 0, 1, 2, and 4. Okay? So 0 can be described as A plus B plus C, and with 1, it will be A plus B plus C prime. 2, plus 2 is A plus B prime plus C. And what will happen here for the last one, which is 4, 4 will be 4, the code for 4 is 1, 0, 0. So A prime plus B plus C. All right? So that is the product of sum for this one. And if you want to simplify it, okay, at the end of the day, it will be close to what we got there. So F will be equal to, instead of having AB, it's going to be A plus B and A plus C as well as and BC. Okay. Now, if you would like to implement that, so we wrote the function as a product of sum. If you would like to implement the function with NOR only, we will do what? Guys, we will do just De Morgan, or we use the shortcut, but in an inverted way. In other words, so that is A, and this is an or, okay, with B, and we have A ORed with C, and we have B ORed with C, with the B ORed with C. All of them are ANDed. So what we can do here now, what we should do is put a bubble here, bubble here, bubble here. So that's an OR, and a bubble here, a bubble here, a bubble here. Same principle, okay? So this can be replaced by an OR. Why? Look at this. If I complemented F twice, F prime is equal to F, yeah? Now, I can distribute the bar to this guy, and this guy, and I have to change the sign, okay? So if I change the sign, this F is equal to A plus B plus A plus C plus B plus C prime, and remember we have double prime, so, and I distributed just the inner one. I have a big prime here. This is NOR, and the whole thing at the end of the day is NOR. Okay, I'm done. What I'm gonna do is I'm gonna stop my tablet and we will share it on my machine. Okay? Stop sharing. And now I'll be able to see anybody who can ask a question or 3 at the same time. That's very hard for me. So who raised his hand? I will go with Jack first. Okay, Jack? Go ahead, buddy.
Sorry, that was from a while ago. I didn't. I did that when you weren't speaking.
Oh yeah. Listen, I can't hear you because I have to quit myself from this tablet because I did something here, and here I have to go and make sure that the voice is enabled. Now I can hear you. You can ask me again. Okay, Jack. I'm all yours, buddy.
Yeah, sorry, I raised my. I didn't even realize my hand was raised. I didn't have any questions.
You don't have any question? So can you please mute yourself? Because I have a lot of students. I can't find you anymore. Okay, who else raised his hand or her hand? Okay, let me open the chat then. Okay, now you're asking me about the midterm. You know, I don't know when the midterm is. When I finish chapter 4, I will get you the midterm. After module 4, the midterm. Can I pose the physical PowerPoint for module 2? Of course, I'm gonna. But you have to watch the video first. So when we use NOR, or we use product of sum, right? Yeah, it's easier for you to convert from a product of sum to NOR, to a NOR only solution, okay? Because this will go with De Morgan's, you know, De Morgan's second law. No, attendance is not being attended yet, like it's not being taken yet. At the end, I'm gonna get a report from Zoom. So you wanna leave? Go ahead, you can leave. What's the time now? 1:14. Yeah, you can leave. Will the midterm be like the assignments? I want to make sure everybody will fail this course. So no. Of course, yes. Yes, you are allowed to repeat inputs on the exams, but on the assignments, don't. On the labs, you will not be able to do it. On the assignments, yes. Go ahead, no problem. Okay, what kind of form? You have to go to the course outline, and that's it. Don't ask me anything about the midterm. I already answered this question. Okay, guys, any questions? Anybody who wants who wants to talk directly to me, please let me know. I know what we should already know, but this is, can we quickly go over the difference between the literals and the term? Of course. Of course. Just give me a second. Give me a second. So the term can be either a min term or a max term. No, this session will not be posted in the Brightspace. First of all, because I did not do it like we had some problems, and this is a synchronous session, so it's your problem to watch it, or maybe like I will be good and post it. I don't know. I don't know. So okay, just give me a second. So I will do it. I will make sure that you're good with the term and the midterm. Okay. Share. I'm gonna share a whiteboard. Can you see that? Who asked for? Yes. Can you see the whiteboard? Can you see the whiteboard, please? Yes. Okay. So if you have, okay, this thing, start, please. Yes. So if you have an F, which is A, B plus AC, that's a term, okay? But this is not a min term, neither a max term. All right? Now, the literal is the variable or its complement. So if I have A, B, A, C, I have just 3 literals. But what about if I have A, B prime plus A, C plus A, B? So how many literals? How many terms? I have 3 terms, and I have just 3 terms, and I have this is a this is a variable, and this is a variable, and this is a variable. Okay, as well as this is what? This is the complement of B, so it can be considered as a literal. So we have 4 literals. Okay. Oh my God, you cannot see any. Okay, okay, okay. So if I bring it here, did you see anything here? No? Okay. Yes? Now we can. Okay. So, okay, let me go again. So we have a function f, and it's AB plus AC. Now this function has 2 terms, AB and AC. The literal is the occurrence of a variable or its complement. So fortunately here we don't have complement. So we have 2 terms and 3 literals, 3 variables. However, this one, okay, F, this is G. That's not F. G here has 1, 2, 3 terms and has 4 literals because B is being described as a B and B format, B prime. Is that clear? Clear? Yeah, no. The literals is the wider umbrella because literal will include the variable and the complement. The variable is A is a variable and A prime is not a variable. It's still like this function f. Okay, I can't. Okay, where is welcome? Just give me a second, guys. Mapping screen to 3. Okay, now I can write on the screen. Now, go ahead now. Okay. Mapping. Yeah. So why I cannot write here? Yeah, I have to move it. Okay, 1 second, guys. 1 second. I'm gonna stop sharing and then I will share again, so it will be easier for us to walk. Mapping. All others. Just monitor. Okay. Good. So now share whiteboard. And the whiteboard is, no, I'm gonna share that screen here. I'm gonna do this, and I'm gonna share this screen, which is the, yes, this one. So can you see the OneNote here? If you can see the OneNote, then that means I can write. Okay, so so the function f, like here, function f equal ab plus ac. Okay, this function has just 3 variables because it should be written as f of a, b, c. Okay, and f of a, b, c can be equal to ab plus ac plus ab prime. Okay, now this function, like f2, let's say, because those are not equal to each other. If I'm gonna use the consonance theorem, no, I have to keep the, if it's like this, a prime, yeah, that might work. Okay, so this function here has what? Has 3 variables, 3 terms, and 4 literals. Okay? Why 4 literals? Because we have A, B, C, and we have B prime. Now let's suppose we have again here plus, or you know what, without a plus. Let's suppose here we have it AB prime, C prime. So we still have 3 terms, 3 variables. However, we have here 5 literals because C occurred or appeared as the true state and the negation state. This can be referred to as, this term can be referred to as a min term. All right? Stop sharing. Okay. Yeah, sure. No problem. No problem. I'll do it. Anybody else? What about the lab, guys? Are you okay with the lab? Are you comfy with the lab? So now I've posted some guidelines to show you how to install Quartz. Okay? Yeah, it's too low because your machine is weak. I'm sorry. You don't have resources. Try to do it. Okay, and even if you do it on the, it depends on how many students are using the remote app at the same time. Can we be alone for the lab? Just contact a lab, you know, for that. I don't, I will not look at the groupings anymore. I'm gonna buy a new laptop. No, just use the VM, like the remote apps, while everybody is not using it. That's it.
Just had a quick question.
Okay, go ahead.
For since labs are in groups, do we only submit 1 copy per group?
Yeah, just 1 copy per group.
Okay.
Anybody who wants to talk to me? Yeah, for the figures, just the figures extracted. Okay, I'm gonna show you how to extract the figure. Okay. Okay, now let me ask you something. Do you like live or recording? What do you like more? Recording, huh? Live. So should I, okay, should I make a survey? And I will go with, should I make a survey? Recording with live review at the end is good.
I mean, if you do a live session and record it, it's sort of the same thing then.
Recording can have distractions. Okay, one live for every module. So we will stick with that, okay? And for, okay, you want me to stick with the time zone and take attendance, or I will post it whenever I feel like it and no attendance? For the timing, I mean. It's gonna be at the night time. Yeah, if it is off the school schedule, no attendance. If it's on the school schedule, I will take attendance. Okay, so we will stick with that. We will stick with the rules. We'll stick with the rules, okay? So now let me show you something here. Speak up in the recordings. Oh yeah, okay, man. The voice is very low. Oh, okay. We'll try to fix it. I'm not a YouTuber, man. I don't have a special mic for that, but I will try to magnify it at the end. I don't want subscribers. I don't want nothing. All what I want is just to finish the course with you. Just let me show you the quartz, how you can extract something, how you can get the figures for that question. Okay, so yeah, share. I will share screen one that has quartz. Okay, can you see? All right, so we have the file. Easy example, okay? So you wanna extract this one, okay? So file, you have here export. You see that? JPEG or bitmap. See how it's easy? And it will be high quality. Okay? Stop sharing. So anybody else who wants any questions? If yes, go ahead. If no, you can leave. It's okay, no problem. I will not count this attendance as well. Yeah, no problem. Oh, thank you. When I start course, should I choose a new project or an existing? If you already have made a project and you want to do some modifications on the file inside it, you don't need to create a new project. Okay? But if you want to do something new, let's suppose for lab 2, yes, you need to create a new project. Now, if you encounter the problem because you don't know how to select a top-level entity, just create a project for each diagram, okay? In particular, a question, but I was wondering if you received my email. I have some questions to ask. Okay, just give me a second. Okay, buddy, like your email is generic. So I post everything as a recording, so you can catch up anytime you want. That's it. Okay? That's it. That's what I got from you. Just that you are like, you're enrolled late. And as a matter of fact, I told the registration to open it, to open the register, I told the university to open the registration because I don't want the people who got their marks late to be stuck till next winter. Okay, here, huh? Yeah, the labs. Have you got your grade from the other prof? If yes, I will waive it for you. Just ask him to send me the grade. Is that good? There are 5 inputs, and A and C are connected to the first gate. Perfect. Okay, who has a question, guys? Now the number has been shrunk a lot. So who has any question? If you have a question, let me know. If not, you can leave. Can you please clarify what's the input for the circuit in figure 5? Okay, any questions for the labs, contact my TA for it. Okay? He's responsible to answer because they will grade it. Mariam. Okay, thank you. Ask Ala, my head TA. Okay, listen. If you are okay, that's the way you have to. We have to do the communication. Okay. Now, first you have to do it on Brightspace. Secondly, on the discussion. Okay. If you're not, who is that TA who said that he's not sure? Can you send me an email? That's it. Send me an email. So if the TA did not answer you and you're not satisfied, you have to contact Ala. After Ala, if you're not satisfied with Ala, contact me, please. Send me an email as an exception, I will answer you. Okay, guys, I'm gonna end up the session. Thank you so much for joining, and I hope everything was clear to you. Have a nice day.